Now, just as a reminder, something you know already, the difference between subjects ANOVA and repeated measures ANOVA is in a between subjects ANOVA, you're looking between the subject groups. You're looking at multiple groups, different people in each group, and saying, is there a difference between the subjects in these different groups? So between subjects, we're looking between the groups. Are there differences between the groups? Does that make sense? In a repeated measures ANOVA, what we're asking is, if we take the same people and repeat these measures over and over again, are there differences time 1 versus time 2 versus time 3? Are there differences across conditions? This is a video describing a particular situation, again from the text, where you will be performing a repeated measures ANOVA. So we'll start by going to the menu, opening up a data file for this. This is the Broca's aphasia file. You can find that midway down the list, down here, Broca's aphasia. Once that opens up, we can talk about how these data look. We've got 6 participants here, numbered 1 through 6. And what we've asked them to do is we've assumed that they have had some kind of stroke, and presumably they've got some deleterious effects from that stroke. And so we measured their speech performance as the first variable, their conceptual performance as the second variable, and their syntax or command of language as the third variable. So some people might be able to get stuff out when they speak, but they might be very ungrammatical. It might be broken sentences. Some people will be able to kind of get speech out, but it won't conceptually make sense. And so different kinds of aphasia will have different kinds of impacts on people. And when you look at these 3 variables, you can assume that they're on the same scale and that they've been standardized so that it's appropriate to compare them. If they're not of the same scale or the same type of measure, then it wouldn't be appropriate to say, like, for instance, is the mean of this variable that's on a scale from 0 to 100, is that different than this other variable that's on a scale from 1 to 7? Well, because obviously the means are going to be different. You have to assume when comparing the means across different measures in a repeated measures ANOVA that the measures are assumed to be the same. And if there are differences between them, it's because of the thing you're measuring, not because of the measure itself. So in this situation, they're all on the same scale. They should be equivalent if the people had the same degree of competence in all of these 3 areas. So the first thing, as always, what we want to do is to go to exploration and run some bar plots so that we can understand what's going on here. Just big picture with the data. The first thing you'll notice is that the conditions here, or these variables here, are not coded appropriately. So these are listed as if they were categorical variables. See these icons? That suggests we have to go back and fix them so that they're continuous variables. So I'm going to go to the data, I'm going to open up the speech and change it to continuous and do the same thing for the other 2 variables, because these are dependent variables. They're on a scale. They're not the numbers here, like an 8, a 7, and a 9, they're not different conditions. That doesn't represent different kinds of things. It's all on a scale, so we have to tell the computer that these are scale variables. Okay, going back to our analysis, I can reopen up my descriptive statistics now, and I can take these and perhaps consider plotting them within my variables list. But problematically, if we ask for the bar plot down here, what it's going to do is it's going to treat each of these 3 as if they were different variables. So it's going to give me a bar plot for each one, and that's really not helpful. It's difficult to compare those 3 against each other because they're not on the same y-axis. Like this one caps out at 6, this one caps out at 8, and this one caps out down here at 5. And so when you look at them, they all look like they're the exact same height, but the difference is they're not on the same y-axis. So this is not helpful. Let's scratch this. by just right-clicking here, and I'm going to click all. I'm going to select all and remove. I don't want any of that crap what we just did. Instead, I'm going to rely on the repeated measures ANOVA protocol to give me a plot instead. So I go up here to ANOVA. I go to a repeated measures repeated measures ANOVA, the third one down. And in that protocol, in that paradigm, we've got a different setup here than before. Unlike what we had before, where we could just slap together some quick variables, I have to define for the computer what the repeated measures variable, or factor, is. So in this situation, we've got 3 different kinds of tests. We've got a speech test, a conceptual test, and a syntax test. So I'm going to come up here where it says repeated measures factor 1, and I'm going to say this factor is the test type. And then under each of the levels, I'm going to say the level for the first one is speech. I'm going to drag that over. The level for the second one is conceptual, drag that over. And the third one is syntax, drag that over. So it's not dragging over right now because I haven't defined a level there. Once I've defined a level, level 3, then it creates a space for that to go over. So I'm going to come up here and I'm going to, rather than just naming these levels 1, 2, and 3, that's not very helpful. I could name them the same thing as they're named down here, or they don't have to be. I could use abbreviations, or I could use descriptions or something like that, but I'm just going to call it the same thing for the sake of expediency, because these variables are already named intuitive types of things. So I'm going to call this speech and conceptual and syntax. Alright, so now what we have is I've defined for the computer that we've got a test type variable and 3 different types of tests within it. And then I've told it which variables match up with those levels. I've said speech, conceptual, and syntax line up with levels 1, 2, and 3. Now, we could also use a between subjects factor if we had one, and if we were doing a factorial ANOVA, but in this situation we're not, because we're just dealing with one-way ANOVAs. We're just dealing with one independent variable. And so that's all I'm going to plot up here in the boxes. Then I'm going to scroll down, and I'm going to ask for assumptions to be checked. If we open up our assumptions checker, we see that there's a type of assumption here called a sphericity test. Now, sphericity is just basically the name that we give to homogeneity of variance assumption within the repeated measures ANOVA paradigm. Why do we call that? Because it's not really homogeneity of variance. It's something that's conceptually very similar to that, but it's the variability within the 3 different groups within the same people. So sphericity is measured slightly different than variance, because variance assumes that the 3 different groups are different groups of people, but sphericity assumes that they're 3 groups of the same people measured multiple times, and so there should be a high degree of relationship between measure 1, measure 2, and measure 3, because it's the same person doing each of those measures, so it kind of accounts for that consistency across measures, and then we call it sphericity instead of homogeneity variance. But we still need to test it, and so we just check that box there. It will come up with a sphericity test, and if we look here at Mauchly's W, that's the first thing we want to see. Is that significant? So we look here at the statistic and the p-value. This is not significant, so we don't have to worry. We're good to go. But what if it was significant? Because sometimes in your homework you might find that you need to run this kind of statistic, and you might find that you violated the assumption. Let's assume for a second that this actually was statistically significant. It was less than 0.05. That means you violated the assumption of sphericity, and the variability across the 3 conditions isn't the same. In that case, you would have to come over here to the greenhouse geyser and the Hohenfeld to see which one of those you would need to use as a correction. If the greenhouse geyser is greater than 0.75, then you need to switch over here to the Hohenfeld. This is greater than 0.75, so in this situation we would come over here to the Hohenfeld. If it's less than 0.75, then we would use the greenhouse geyser metric here. Now the metric itself doesn't mean anything, it doesn't do any good, but what you do need to recognize is if you've violated the assumption of sphericity, then you have to make a correction, which is listed right here, sphericity corrections, and you don't know which kind of correction to make without looking at those values. So if the greenhouse geyser effect is too high, like it is in this situation, above 0.75, then you have to click on the Höhenfeld correction, and that will bring up a new ANOVA result up here that gives you the Höhenfeld, and it gives you the new F and a new p-value. Now in this situation, it's the same. Why? Because we didn't actually violate this assumption of sphericity, and the correction didn't really do much. If we had a greenhouse geyser that was less than 0.75, then we wouldn't select the Höhenfeld, we would select the greenhouse geyser, and it would run an altered ANOVA up here. Again, not much of a difference. The p-values are almost exactly the same, but sometimes if you have really violated the assumption, then they might be quite substantially different. I never can remember the greenhouse geyser procedure here, this 0.75. I don't expect you to remember that. What you should know is the power of Google. If you ever don't know what to do, how to interpret any of this stuff, just Google, like, how to test sphericity, and then how to interpret sphericity output, and Google greenhouse geyser, and you'll forget this stuff. I promise you'll forget. I forget it. I have a PhD in this stuff, and I still don't remember all of it. But when I have to run an ANOVA of a repeated measures type, then I just go and Google, how do I run this test of sphericity? How do I interpret the greenhouse geyser and Höhenfeld? And it tells me what to do. Okay, so in this situation, we don't need either one of those corrections. We're just going to ask for the no correction version of the ANOVA, and we're just going to assume that we've got equality of variances. This test right here is only useful for if you have a between subjects factor listed here. If you don't have a between subjects variable, then equality of variances is irrelevant. Instead, you're measuring sphericity only. Okay, so once we've tested our assumption, we know that we haven't violated sphericity, then we can go back up to our ANOVA and we can say, okay, we've got test type as a variable. Did that have a significant impact on people's results for those different tests? The F statistic is pretty large. It's far bigger than 1, which is what we'd expect it to be just by chance. The p-value is less than 0.05, so we have to conclude there is a difference between some of these conditions. Now, right now, like I said before, we tried to go and run some explorations, some bar graphs and stuff like that. We couldn't do that, so we don't really know what the mean differences look like. We haven't asked for descriptive statistics or a bar plot or anything, so we don't know what the means look like for speech, conceptual, and syntax. In order to know that, we should come down here to where it says estimated marginal means, open up that box, and then you can request test type over here as the request that you're doing, and it automatically plots for you because this is checked. Marginal means plots. Marginal means just mean like the means for different groups, ignoring the overall. So it's the means for the subgroups. So here we've got the bar plot that has a mean of around 7 for speech, a mean of around 6 point something for conceptual, and a mean of around 4.5 or so for syntax. So you can see that the error bars are drawn. They're pretty wide, so they overlap quite a bit. And if we were to make a guess here, we know from the ANOVA up here that there is at least one mean difference. And if I were to guess about that, I would say probably speech is different from syntax. But we don't know for sure if speech is different from conceptual, if speech is different, and if conceptual is different from syntax, right? So in order to know those, we have to run post hoc tests. We have to figure out where is the mean difference. In order to do that, we're going to come over here and open up our post hoc test box. We request our post hocs for test type, and of course, as you already know, we're going to not request 2 key, but we'll request home instead. Not that it makes much difference, they're all about the same. But once we start looking at this plot of post hoc comparisons, you can see that speech versus conceptual is not significant. speech versus syntax is. Conceptual versus syntax is not less than 0.05, not significantly different. So the only difference here is speech versus syntax, just like we thought. The last thing that I want to remind you of is when you're doing an ANOVA, you need to request your eta squared, and your eta squared in this situation is okay because you're using repeated measures ANOVA. In the between subjects ANOVA, you'd want to use the omega squared, but in this situation you use the eta squared, which isn't biased because we're using the same people across multiple conditions, and you can say that 41% of the variability in the results that they got on the tests is due to which type of thing it is. So the test type accounts for 41% of the differences in their scores on the different conditions. And that is how to run a repeated measures ANOVA.